Okay, let's get started. Yeah, so whiteboard. Okay, so today we'll talk about like Fermat theorem and stuff. So this beginning part's review, right? So for example, given a group G, right? Order of what's the order of element? So this is order of an element. Let's call it A. Is the smallest positive integer n such that a to the n is e. Yeah. So where e is the identity. So does everyone understand what I mean by a to the n? Yes. No. Like what does a to the n mean? Hopefully. Yeah, but the people normally think of it as is not times, right? It could be times, but it's by it's star. So again, I didn't write this, but it's whatever the operation is, right? So like this is like a star. So it might not if the operation was times, then yeah, it is what you think, right? But it's the group operation, right? So for example, like z mod nz under plus, right? 1 to the n is 1 plus 1 plus 1 plus 1 n times, right? Yeah, does everyone understand? So you shouldn't think of this as, multiply. You think of it as, whatever the group operation is. So yeah, okay. just clarifying that because I feel some people might mess that up. So okay, so if no such n exists, we say order is infinite. Yeah, order is infinite. And hopefully you remember from Math 120A, there's Lagrange theorem that order of an element must divide order of group. So really this is only useful for like, how do I say it? Non-finite groups, right? Because if your group is infinite, anything sort of divides infinity, right? Lagrange is kind of useless. But so it's really for like yeah, finite groups. So example, right? Let's take z mod 6z under plus. Order is infinite. order is infinite, like infinity is infinite. Okay. Yeah, I mean, by the way, like, I guess you're asking because you're taking notes, maybe. I post these vids on YouTube, so just you could check it out on YouTube if you missed anything. Okay, so I'll just write O for order. Yeah. So what's the order of 1 in Z mod 6Z? 6, yeah, because you have to add 1 to itself 6 times to get 0, right? What's the order of 2? Good. Order of 3? Good. Order of 4? Yeah, 3, and then order of 5. So 5's coprime, right? So that should be 6. Good. And finally, order of 0 is just 1, right? Order of identity is always 1, right? So you see here, right? All of these are divisors of 6, right? So this is what Lagrange says, right? Order of an element must divide order of the group. The order of the group in this case, how many elements does Z mod 6Z have? It has 6, right? So you know every element must have order either 1, 2, 3, or 6, right? So like no element is gonna have like order 4 or order 5, right? You must divide 6. So that's pretty strong, right? So okay. And obviously for infinite groups, right? Anything can happen, right? So here you can see that like all elements aside 0 have infinite order, right? If you take any number any integer other than 0 and you keep adding it with itself, you're never getting 0, right? You're just gonna either go off to infinity or negative infinity. Okay, so here comes the sort of like the fun part. So we need one more thing to get into like Fermat little theorem and stuff like that. So it's this part. I'll let you. I'm not gonna prove this, but I'll let you work it out yourself. It's not that hard. So given a ring R plus, under plus and multiply with unity, right? Um, the set of units. So do you all remember what units are? So these are things with inverses, right? So these are stuff with like, an inverse under this operation. Units of R form a group under multiplication. Yeah, so you could check this. So an example would be, let's just see some examples, right? Let's take this ring. What is the set of units here? Which elements in Z are invertible under multiplication? Yeah, 1 and -1, right? So this forms a group under multiplication, right? I mean, you could check it's closed, right? Because 1 times -1 is -1, -1 squared is 1, right? I mean, in fact, you could check that if you like, if you're interested. This is actually isomorphic to Z mod 2Z under plus. I'll let you think of what the map is. I mean, you only have two choices, right? There's like two elements. So you either map, and you must map, identity to identity, right? So the identity here is 1, the identity here is 0. So you obviously map 1 to 0 and -1 to 1. Okay. What about Z mod PZ under plus multiply? What is the units in Z mod PZ? well, so let me say P prime. Yeah, when I write P, P is prime. Yeah, all non-zero, right? So this is minus 0. This forms a group under multiplication. In fact, later on, you will see that. So let me say group. This is group. So let me just say later on, you'll actually prove that, it's cyclic. And in general, it might not be, right? But if it's a field, it's gonna be cyclic. But never mind that. So let's continue. So that's what we need, right? So if this is a group, right? What does so this is Fermat little theorem. Let me just say. This is corollary. I'll keep it here because I wanna corollary of Lagrange. If this is a group, what does Lagrange tell me? The order of an element must divide the order of a group, right? What's the order of this thing right here? How many elements does it have? P minus 1, right? So what you're gonna see is given A in Z mod PZ without 0. You can actually check that A to the P minus 1 is congruent to 1 mod P, right? So A to the P minus 1 is E. Why is this? Well, I know the order must divide P minus 1, right? So order of A must times some number K is P minus 1, right? For K in positive integers. Then A to the P minus 1 is A to the order of A times K, which is A to the order of A. I could, just work with this first. But what's A to the order of A? By definition of order, what is it? Order is the smallest positive integer. So what is A to the order of A? So here, right? Recall an order of an element A is the smallest. Yes, identity, right? So you see here that this is just, in this case, identity is 1, right? 1 identity for this thing. I mean, obviously you're multiplying, so identity is 1, which 1 to any power is 1, right? Do you all see this? So in fact, take any element in Z mod PZ without 0. You're gonna, if you raise it to the order of the group, you're gonna get identity, and it's a corollary of Lagrange. Do you all follow so far? Okay. So, okay. So this is exactly Fermat little theorem. There's basically a name for it. So if A is in Z and P doesn't divide A, then we have this, right? So this is just reformulating what we did like 10 seconds ago. So why the P doesn't divide A? If P divides A, what is A when you mod P? If P did divide A. Yeah, it's 0, right? And we were working without 0, right? So this is just saying exclude all the things that's 0 in Z mod PZ. which precisely means you're not divisible by p, right? So yeah, so this is Fermat theorem. And then you have a corollary, right? If you want everything to hold for including 0, well, let's multiply by a on both sides. We have a to the p is congruent to a mod p. So from Fermat theorem, you know this holds for p doesn't divide a. But if p did divide a, this is still true, right? Because 0 to any power 0. So you have that this holds for all a and z. Okay, so that's for primes, right? What about non-primes? So z mod nz plus multiply. What are the units in z mod nz? Now, n is like an arbitrary positive number. Yeah, so let me just say the class of coprime numbers, yeah? So basically, there's a word for it. Phi of n is number of positive integers coprime to n and less than n. Yeah, like less than n because we basically, like, if you mod 12, right, 1 and 13 are like the same thing, right? So you don't want to if I don't include this, like, you'll be including 1, 13, 25 stuff, and like there'll be infinitely many, right? So this is called the Euler phi function. This is a function, right? So some books, call it Totient function. I don't know why, but Euler Totient function. And by same thing, right? So similarly, exactly by corollary of Lagrange, right? If A is relatively prime to n, A to the phi of n is congruent to 1 mod n. Yeah. The order of the group here was p minus 1, right? The order of z mod p z without 0. The order of this is exactly, we defined it to be phi of n. So a to the phi of n is congruent to 1 mod n. So this is called Euler theorem or something. So it's more general, right? So this theorem includes this one, right? Because phi of p is p minus 1, right? What are the positive integers coprime to p and less than p? Well, 1 to p minus 1, right? So yeah. Is everyone clear so far? Yes? No? Okay. Yeah, so kind of a lot to take in. We'll do examples, yeah? So let's do some examples. So if your friend asks you, like, what's the remainder when you divide 23 to the 43rd power by 23, right? Because again, when you mod 23, whatever it is, it's just the remainder, right? So if your friend asks you, what's 3 to the 43rd power? Like, when you divide that by 23, what's the remainder? You don't want to multiply this all out, right? But this is actually doable because I know that 23 is prime, right? So I know a to the p minus 1 is congruent to 1 mod p, right? That was the theorem we just went over. And a is certainly not divisible by 23, so this holds. So what do I know? From this, I know that 3 to the 23 minus 1 is congruent to 1 mod 23, right? So I know 3 to the 22nd power is congruent to 1 mod 23. So what's 3 to the 43rd? Any ideas? What is, how do I say it? So I could simplify this, right? Yeah, this is 3 to the 22 times 3 to the 21. So basically, I could say this, right? Is congruent to 3 to the 43, right? Or let me put it on the other side. So I know that this is true, right? On the other hand, I know this is 1, right? So this is 3 to the 21 mod 23, right? Now let's figure out what 3 to the 21 is. Well, let's multiply by 3 inverse, right? If I multiply by 3 inverse, I get 3 to the 21 is congruent to 3 inverse mod 23. So all you need to do is figure out what the inverse of 3 is. So this is congruent to 3 inverse mod 23. So what's 3 inverse? It's actually not hard. What number do you multiply to get remainder 1 when you divide by 23? 8, yeah? There you go. That's your answer. Yeah. So if you get these questions in your like quiz or midterm, right? Please do not multiply this all out. In fact, I don't even know if a calculator can do that. It might give like overload, but like use from here. Multiply 3 inverse on both sides. Right, 3 inverse times 3 to the 22nd is 3 to the 21st, right? I mean, if you like, if this is confusing for you, 3 to 22 is 3 to 21 times 3. Yeah, multiply by 3 inverse. Yeah. Oh, because this. 3 times 8 is 24, right? So 24 when you divide by 23 is 1. Yeah, so it's pretty neat, right? So you see this is quite useful. Let's do like 2 more. Example. I think you have some of these on your homework too. So mod 7. Let's do one more prime, yeah, and then we'll move to non-primes. So what do I know from here? There are a few ways to simplify this. Let's do one thing, right? I mean, like I can always make this a number between like 0 to 7, 0 to 6, right? So yeah, 49. So 37 to the 49th power. So so basically think of it like your friend's asking you, like, take 37 to the 49th power divided by 7. What is the yeah. In fact, we could do something better, right? What's 37 mod 7? What's the remainder when you divide 37 by 7? No. 37, 2, right? Because 7 times 5 is 35, right? So this is actually just 2. So this makes life easier. So I guess I'll just put mod 7 at the end. Yeah. So this is congruent to 2 to the 49. And now I know that 2 to the 6, right, is congruent to 1 mod 7, right? So I could split out factors of 6, right? So this is actually, I could split out 48, right? Because this is 2 to the 6, 8 times 6 is 48, right? Now I know 2 to the 6 is 1. So this is 1 to the 8 times 2, which is just 2. Yeah, because 1 to the 8 is 1. Mod 7. Everyone follow? Yes, no. You don't need to choose 2. It's just simpler, right? Like why work with 37 when you could work with 2? Because remember, elements, like kind of like mod 7, right? Like 1 is the same as 8, is the same as 15, is the same as 22. So I mean, would you work with 22 or would you work with 1, right? I mean, you might as well work with the small thing, right? Kind of like the previous question, right? If right, if I change this to 26, right, it's the same thing, right? Would you work with 26 to the 43 or 3 to the 43, right? Like might as well work with the small one, the small number. Okay, so 7 to the 1000 mod 24. So your friend says take 7, raise it to the 1000 power, and find remainder when dividing by 24. Okay, so here, right, what's in this case is not prime, right? So if it was prime, we know it was p minus 1, right? Like like what I wrote above, 7 minus 1 was 6, right? So here, right, unless you remember the formula for the Euler phi function, I mean, you could certainly wiki it. This one is small, right? We could list it out. So which numbers are co-prime to 24? We have 1, 2, no, 3, no, 4, no, 5 is co-prime, right? 6, no, 7, 8, 9, 10, 11, 13, 17, 19, and 23. Yeah? Do you all agree that like these are the numbers co-prime to 24? How many do we have? We have 8, right? So I know 7 to the 8. So again, let me just say, from here, I know phi of 24 is 8, just from counting. Yeah, so I know 7, so I'm using this, right? So I'm using, where is it? I'm using this now, right? A to the phi of n is congruent to 1. So basically what I was doing before was I was calculating what phi of 24 was. So it's 8. So I know 7 to the 8 is congruent to, whoa. And obviously 7 is co-prime to 24, congruent to 1 mod 24. So how much, so divide 8 by 1000, what do you get? What's 8 divided by 1000? So I have 7 to the 1, 22, 45. Does it go perfectly? Or, oh, it goes perfectly. Oh, okay. So this is 7 to the 8, 125, which is 1 to the 125, which is 1. There we go. Not that hard, right? Everyone follow? Hopefully these questions will be easy by now. So I'm going to go over one of your homework questions for next week, yeah? But before that, we'll do a easier one. Just to see, you know, how it's one of the theoretical ones, yeah? So let P be prime. So the question is, this is not the one on your homework. It's the next one I'm going to go over, but it's similar. So we'll tackle this, and then we'll go over as a class, you know, how to do the next one. So it says calculate Euler phi function of p squared. So basically it's asking how many numbers are coprime to p squared. So question, are numbers so let me put it this way. Let's see which numbers are not coprime to p squared. Yeah. So let's count. So what's the smallest number? Can it be 1 to p minus 1? Can any number between 1 to p minus 1, are those, can they share a factor with p squared? No, right? Because first off, if you share a factor with p squared, then you must share a factor with p, right? I mean, it's like, because you either divide p or the other p. In which case, but p is a prime, so it's not possible for a number between 1 and p minus 1 to divide p, right? Because p is a prime. So you see your first candidate is p, right? What is the next one? I mean, if you divide this, you must have p as a factor, right? Pretty much. So you must have 2p, right? 3p all the way to what? Jacqueline. Yes, p minus 1, right? P minus 1 times p. And finally, p times p, right? Which is p squared, right? Is everyone clear on this? So basically, we just do this. Take all numbers from 1 to p squared, right? And subtract off, or I guess subtract's the wrong word. Take off those not coprime, right? To p squared. So there are p squared numbers from 1 to p squared, right? And how many numbers are we taking off? How many numbers are here? P. Yeah, and that's your answer. Everyone follow for this? Yes. So this is how, I mean, that's how I would think about it, but I'm sure there are many ways to do this problem. So, okay, so the next one is your homework question. So it's a bit harder. Let PQ be distinct primes. Basically calculate phi of PQ. So obviously, what are two obvious things that divide PQ? So again, we are gonna find those not coprime to PQ. So what two numbers obviously divide P times Q? Good. Okay. Now, what other numbers can divide P times Q? Let's start with here, right? What number is has P as a factor and divides P times Q? No, not divide, but not coprime, right? So they what numbers share a factor, right? Not divide. That's the wrong word. So obvious 2p shares a factor with PQ, right? So it's not coprime, right? So what else? So I started you off. What other numbers? Right? Because if you like GCD of PQ and 2p is like at least like p, right? If q is not 2, right? At least p, say bigger than 1, right? So it's not coprime. So it's like this, right? 3p, 4p, all the way to what? All the way to q minus 1p and then qp, right? Now you do the same for this. So what about this side? I have 2q, 3q, all the way to what? So PQ, right? Everyone see this? Everyone follow so far? And these are it, right? So let's take all numbers, right? All numbers, which is just PQ of them. All numbers from 1 to PQ, there's PQ of them. Now we subtract off how many numbers are here? Not exactly, Shiyu, but let's work with this. How many numbers are like right here? Q of them. How about here? How many numbers are in this row? P of them. Now, am I double counting any? Yeah, we counted this twice, right? So we got to add one back, right? Because we subtracted that one off twice. And sure enough, this is your answer. But if you want a more better expression, it's this. So you could check for different primes. It's actually just this, right? Because Euler phi of P is P minus 1. Euler phi of Q is Q minus 1. Okay, does everyone follow so far? All right, good. So now the next thing would be, what about system of equations, right? So solving equations in Z mod MZ. So there's a theorem, right? It says let A be relatively prime. Some books say relatively prime. It means coprime. Yeah. So prime to M for each B in Z mod MZ. AX is equal to B has unique solution in Z mod MZ. What is the solution? You all know this. Like if I gave you, right, an equation like 2x equals 1, how would you solve? How would you solve for x? It's not a trick question, by the way. Yeah, you divide two, right? So same exact thing here, right? Except what is divide in Z mod MZ? Divide is multiply by inverse, right? So all you're doing is, I mean, it's clearly unique because all you're doing is you're multiplying by A inverse on both sides, right? I mean, x is, sorry, this should be congruent. A inverse B mod M, right? Do you all see that? So now you sort of see why we need this part, right? It's because when you're relatively prime to M, what does that guarantee? It tells me the inverse exists, right? It's a unit, right? If we didn't have this assumption right here, it might not be possible to multiply by A inverse, right? Because A inverse need not exist. Everyone clear on this so far? So it's sort of exactly like how you would solve an equation in Z, right? Except, this thing has to be invertible, right? Because like an example would be like mod 2, right? If you're working mod 2, x has no solution because this is saying 0 is 1, right? This is your solution. X is A inverse B. That's the solution to the equation, right? Yeah, you really don't have any other choice. But you see here, right? You need not have solutions like here, right? I mean, if I was working mod 2, right? This is impossible, because 0 is not 1 in Z mod 2Z. So you see, you do need this relatively prime thing. Okay, but it is possible to be, what if you're not coprime? If not coprime, right? So it asks Ren, do you have a solution? So A, B, and Z mod MZ, right? D is GCD of AM. So AX equal to B has solution in Z mod MZ if and only if the GCD divides B, right? So this is a corollary. This is question mark. This is a corollary of the previous thing, right? Because in the previous thing, A was co-prime to M, right? So D is 1, right? And 1 divides anything. So, but this is the general case, right? So how would you go about finding the solution? So I want solution of this, right? So what they say is this is the same as solving A over dx. Congruent, I'm dividing by D on both sides. Mod M over D. Yeah, and all of these are integers, right? Because we're assuming D divides B, and D is the greatest common divisor of A and M, right? Forget greatest, it's a divisor, right? So it divides A and M. So for example, just to convince you, right? If I'm solving something like this, what does this mean in terms of like actual integers? It means 2x minus 2 is some multiple of 6, right? Because if I subtract 2 on both sides, I get 2x minus 2 is congruent to 0 mod 6, right? And to be congruent to 0 mod 6, that just means 6 divides it, right? So it means this. So let's divide by 2. This is the same as saying x minus 1 is equal to 3k, which basically saying x minus 1 is congruent to 0 mod 3, and x is congruent to 1 mod 3, right? So in the end, all I did was sort of what I wrote there, right? I sort of divided by 2, right? D is 2, right? Divided by 2 to get x. Yeah. Now this is, now what is GCD of A over D and M over D now? Can anyone tell me? So D was the greatest common divisor of A and M. So if I divide out by the greatest common divisor, what divisors do they share now? Yeah, it's just 1, right? So this has unique solution by the previous thing I did, right? Right here, right? This theorem. Because now GCD is 1, I'm relatively prime. So I have unique solution, right? Just multiply by the inverse. So from here, and it turns out, let's call it x1. Then all your solutions are given by x1 plus m over d, x1 plus 2m over d. So this is like a theorem, right? I'm running out of time, so I'm just gonna write it out. You could check all the rest are solutions too. So plus d minus 1m over d. Yeah, so let's sort of do an example on this, right? So let's do something like 39x congruent to 52 mod 130. So the first thing you should do is calculate GCD of 39 and 130. What is that? So 39 is 13 times 3, right? So it seems to be 13, right? Because they share factor. Yeah, it should be 13. So divide out by 13. So I get, this is 13. And then mod, so follow what I just wrote, right? So now it's 3x congruent to 4 mod 10. This is easier to work because, again, now this is coprime, right? 3 and 10 have GCD 1. So this has unique solution, right? Just multiply by 3 inverse. So x is congruent to 4 times 3 inverse mod 10. And all you do is figure out what 3 inverse is. It should be 7, right? Because 3 times 7 is 21. 21 mod 10 is 1, right? So x is 8, right? Because 28 mod 10 is 8. And then so that theorem tells you the 8 is that is like the x1, right? And then what else? x1 plus m over d, 2m over d, 3m over d. What's m over d? So m was this was my m. This is my d. So m over d is 10. So 8 plus 10, 8 plus 2 times 10, so 8 plus 20, 8 plus 30. These are all solutions to this equation. 8 plus 30, all the way to 8 plus d minus 1, so 12 times 10, so 120. Yeah, so you have d solutions. I forgot to write that, but there are d solutions total. Yeah. And I think that's about where the professor stopped. So yeah, I'll stop here too. By the way, do you all have class next Monday? No, right? It's like Martin Luther King Jr. holiday. I'm not sure. Yeah, okay. So I guess in that case, there shouldn't be a lecture quiz on Monday. You shouldn't have one if there's no lecture. So consider it a break. So yeah, so I guess on Tuesday I'll go over what he goes over on Friday, I guess.